So here's the outline for my talk. We're going to talk about this idea of observability to begin with. And to give some structure to my talk, I'm going to have a theme for the talk. And the theme is not some general projective measurement way of collecting information from a quantum system. I'm going to be focusing on weak and continuous measurements, and I'll tell you about what those are in some detail. And that's going to provide the theme for my talk. And once I give you some introduction, if you don't know about that, that's fine. I'll tell you a little bit about it. And then we'll go on to talk about using that platform and the experiments associated with that idea to talk about 3 different estimation tasks. All right, and so the 3 tasks I'll be talking about this morning are, first of all, suppose I have a Hamiltonian that I know, but there's a parameter in the Hamiltonian I don't know very well. How can I precisely determine that parameter in, say, either a rapid or an optimal way from the results I'm getting from the measurement? That's the first task. The second task is how do I reconstruct some initial quantum state that suppose I have many copies of this quantum state. I don't know what it is. I want to interrogate it in some way. And there are some well-known ways to interrogate this state. I'll be talking about some new ways, which is sometimes called quantum tomography. And then the third task is suppose I want to observe or estimate when an error occurs in my quantum information protocol. So there are well-known quantum error correction protocols. I want to address this issue of how to estimate when an error occurs from one of these continuous quantum measurements. Okay. And I want to say at the beginning, so the work here on this Hamiltonian parameter estimation, this is published work, but these last 2 elements are unpublished, so I wanted to share them with you. But the papers are almost done, but I'd be very glad to get some feedback from you at the end of the talk, what you think. If you have any new ideas, be happy to discuss with you. Okay. So what is a generalized quantum measurement, or sometimes called a weak quantum measurement? And the idea is very simple. So usually we have an apparatus, a measurement apparatus that we couple to the system of interest, and we want to arrange it so the coupling between them is sufficiently strong that when I look at my measurement apparatus result, the meter points one way or the other or some variety of positions, and that uniquely correlates with some internal degree of freedom of the quantum state. And all these generalized quantum measurements do is they take that idea and they generalize it so that, for example, if I have a classic Stern-Gerlach apparatus with a spin going through some fringing magnetic field, the average splitting, suppose, is given by these 2 black lines here on the right-hand side. But when I look at some ensemble of results, what I find is that the spread of this spin in position is larger than the splitting of these 2 average spin components. All right, and so when that happens, we can still describe that quantum mechanically, but not as an ideal textbook projective measurement. We have to describe it with one of these generalized quantum measurements. Okay, and so one generic way of thinking about it is suppose I have a system of interest with the green dot and a meter, which is the red dot. I describe them both quantum mechanically. I let them interact over some period of time with some joint unitary operation. Then I projectively measure, say, the meter, and that implements one of these generalized quantum measurements on the system. Okay? And so this is a simple model for how to realize these in a physical situation. All right. So, so there's a well-defined formalism. I'm not going to go too much into the mathematical details. We can talk about that if you like in a little bit. But the idea is that this operator M will act on the system and disturb it in a certain way that's associated with the information I gain about the system. So the information X that I obtain here tells me mostly about the meter, say, but a little bit about the system, and this measurement operator M then tells me how the system is disturbed once I receive that information. Okay, good. So that's a weak measurement. What is a continuous quantum measurement? So a continuous quantum measurement is actually a limit, a physical limit, in which I make many of these weak measurements back to back. All right, so I start out with a particular initial state. I then, say, weakly couple to my system, and I collect some result. We'll call it R0 or R0. And that could be either a discrete or a continuous variable. And when I just collect that result, I learn a little bit about the system, but I also disturb the system. So I have to change my state from rho 0 to rho 1, conditioned upon the state of that measurement. And then I repeat that over and over and over again, R1, R2, all the way up to Rn, and I get this sequence of quantum states of the system. All right, so that's the important thing. These are results by reading the environment, and these are associated quantum system states down here. So the way we describe that is that, again, we can think about mapping this previous state, say rho 2 back to rho 1 via some quantum map, and use here denote both the measurement disturbance I was talking about in the previous slide, as well as some, say, unitary operation that's going on in the system exactly at the same time. So both can be accounted for together. So just some jargon in this literature, this collection of R's, R0 through Rn, is called the measurement record. That's what I'm actually reading out in my laboratory on my device. And the state of all these rows, rho 1, 0, 1, 2 through rho n, is called the quantum trajectory. Okay, so sometimes this is called quantum trajectory theory. And we say a weak measurement is just the limit where the time step in time, this is the timeline between each of these measurements, is going to become smaller and smaller, but also successively the measurement strength is also becoming commiserately weaker, so that this mathematical limit is well defined. But physically, typically, there's no such thing as a continuous measurement. It's only really an approximation to when the time scales of my detector typically are much smaller than the time scales of my system. It's like any stochastic process in that regard. Okay, so that's a little bit mathematical. Let me give you some physical examples of such a system. So one system I started thinking about back, 15 years ago when I started thinking about this kind of physics would be a solid state example. So a lot of this work was developed in the quantum optics literature, but here's a solid state example. So I have, for example, a two-dimensional electron gas. I have gate-defined quantum dots here. So I have, say, a double quantum dot where a single electron can occupy either on the left or the right quantum dot. And I can tunnel back and forth between the left and the right dot. And so that's my quantum system I'm interested in learning something about. And then the thing I want to use as a detector or a meter for this system is I'll simply apply some voltage between source and drain, drive a current through this little channel here called a quantum point contact, and look at the current that's flowing. On average, this current is like, give one value, if I'm saying the left dot, and another value in the right dot, and typically this difference is relatively small, okay? How small compared to what? Well, small compared to the typical noise of the system. So there's intrinsic shock noise in the system because electrons are discrete particles, so the current fluctuates in a stochastic manner. And so because there's this shot noise with spectral density I, that gives me some new time scale in the system. So if I take the ratio of this noise power divided by the difference of these two currents squared, that gives me a time. And this is the time I need to integrate my signal in order to distinguish state 1 from state 2. So a signal-to-noise ratio of 1. So this characteristic time scale is now associated with the continuous dynamics of the quantum measurement. We call it the measurement time, maybe a little confusingly. Okay. So that's a first example. A second example we've been working quite a lot with lately is what happens if I have not say a semiconductor quantum dot, but a superconductor quantum system. And the systems we have in mind are these Josephson junction-based charge qubits, sometimes called transmons. And one example that you can do, kind of experiment, is you can take this Josephson qubit, put it inside an aluminum box, put it down to superconducting temperature so it becomes a cavity to the electromagnetic environment. And then I can put in microwaves in one port of the box, take them out the other port of the box, and use the microwave signal I subsequently amplify with quantum limited amplifiers as the meter that I'm going to be using to interrogate the quantum state of this system. Okay? Good. And what you find when you do such an experiment after the quantum amplification takes place, you get ultimately some voltage trace on your oscilloscope, and it typically looks something like this. So it might look something kind of some noisy thing. Now you might say to yourself, that just looks like noise. How is that some quantum measurement? And the first message to you is that that is the quantum measurement. That is the result, the stochastic result of the quantum measurement. And so that's what you've got to work with in this kind of experiment. That's the baseline kind of signal you have to work with. And everything else is making inferences from that kind of baseline reality. So the first thing you can do is you can just time integrate this signal. And what you find is this is the time integrated as a function of time. And eventually what happens is I start out in a random way, but then eventually, if I integrate it long enough time, I come down and I'm in the lower half of this. I'm below 0. And so if I'm below 0, I associate with that, say, with state 1 of my qubit. And if I'm above 0, I associate that with state 2. So in this case here, if I integrate for a long enough time, I can say, aha, the qubit was in state 2. I've collapsed it to state 2. And the usual rules of quantum mechanics apply there. All right, and so the way we can think about this is if I histogram this integrated voltage for many repetitions, preparing either the system in the ground state or the excited state, I find this characteristic sort of doubled Gaussian histogram. So the red histogram would be, for example, if the qubit is in the excited state. The blue histogram is if the qubit is in the ground state. And I see if I wait long enough time, these two histograms, the red and the blue, become very much apart from each other. So I distinguish unambiguously the two states. But suppose I don't have enough time, or the measurement coupling is relatively weak, then I get this overlapping region where the tails of one run into the tails of the other. And this is this weak measurement or generalized measurement regime where I can't tell for sure, but I get some information about the quantum system, but not complete information. So for example, if I get a result that's here, I'm pretty sure it's in the ground state, the blue, but it has some tail in the red, so it might be in the excited state. So I have to take that into account in my analysis. Okay, good. So one of the neat things about this kind of system is that we can do this quantum trajectory tracking in a very nice way. So this is actually data from this experiment from maybe, what, 4 or 5 years ago. And what you see is you have these various voltage traces going on. And for any one of these voltage traces, I can construct the relevant quantum trajectory. For a single run of the experiment, I get, for example, the block coordinates of the qubit. The blue is x, the red is y, the black is z. And I can see these quantum trajectories undergoing some kind of stochastic random walk. And if you look closely, there are actually two lines. So I think the dotted line is the actual single trajectory data, and the black line is what they do at some point is they come along and they stop the experiment and they say, okay, this theory predicts the state should be this value given that record. How can I test that? So they stop then, and they'll do sort of usual quantum state tomography at that point, using repetitions where the theory predicts it should be the same thing, and then check, is it the same or not? And so the other line here is just the check. It's the continuous tomography showing that, in fact, you can very well track the quantum state for a single run of the quantum trajectory. Okay. All right, so one of the analogies I like to give is that you can think about this process as replacing the sort of textbook measurement process where everything collapses instantaneously to either the upper state or the lower state as something like this. So the analogy I like to give is you imagine you prepare a bunch of butterflies in a cage at one time. I open up the cage, and the butterflies all begin to fly around, and eventually they land on one of two trees. So in the conventional textbook quantum measurement, you would just say the butterfly lands on the left tree or on the right tree with some probabilities. But now with this continuous measurement process, I can actually track in a dynamical way how the butterfly gets from the cage going through its stochastic trajectory to landing, say, on the left tree. All right, so it gives you additional information, and the idea behind this talk is we want to now see what can we do with this additional information. Can we leverage it some way to apply to this task of estimation, which is the theme of our workshop. Okay, so we can do other kinds of things with this as well. So in addition to just measuring and collapsing to either the ground state or the excited state, I can actually turn a drive on, so I have a unitary dynamics at the same time as the measurement dynamics. And there what you see is for no drive, I get this kind of stochastic collapse, say, from the x eigenstate of the Bloch sphere to, say, z is +1. The green, by the way, is just the ensemble average of that. So you just see decoherence, whereas on a shot-by-shot basis, you see collapse to either this state or that state. But now when additionally I turn on some drive, represented by the capital omega, which is a Rabi, essentially a Rabi drive, then in addition, instead of just collapsing, I undergo this kind of Rabi dynamics, but along with some measurement back action as well. So if it were just a pure Rabi drive, this would just be a nice circle that goes around the Bloch sphere, but then there's additionally the noise associated with a quantum measurement that disturbs that. And I can turn that up and actually track the quantum trajectories with both of these guys going on, just like I did before with no drive on. Okay, so once you have that, there's lots of things you can do with this. So one of the things that I like to think about is suppose, for example, I have not just any quantum trajectory, but sub-ensemble these trajectories. Suppose that, for example, at t equals 0, I prepare my states in one particular state, and then I measure for some time, and I say, I'm only going to think about trajectories that end in some final state. And then I can ask myself different questions about that. One of the questions you can say is, what's the most likely path that goes between the initial state and the final state? And indeed, we can develop a formalism to predict that, and we're able to then compare that with the experiment, and we get some very nice agreement between that idea of a most likely path between any two initial states and final states. Okay. But that's not the main focus of my talk. But I want to give, before I get to there, I want to give another example. And this is also a very nice example we can think about in the atomic system, which is the fluorescence system. So usually with the fluorescence, you have an atom, like in the lights up above, that you excite them, and eventually light comes out of the atoms, and we see that as a fluorescence signal. What we can do now is we can put this fluorescing atom inside of a cavity and channel the fluorescing light into a coaxial cable, amplify that coaxial cable in some way. In this case, it's a heterodyne measurement technique, and then read out what the atom is doing based on the fluorescence of that signal. Okay? And so there are a couple of different groups that are doing this. Since I'm in the great nation of Paris, I want to especially mention Benjamin Huard's group. At the time he was in Paris, now he's gone over to Lyon. He has these nice experiments where you do exactly what I was talking about. You have radiation from an atom, you collect it, and then you track the quantum trajectories associated with the atom from that fluorescence. Also, Kater Murch in Washington University in St. Louis does a very similar kind of thing, also using this system. And from that, you can do lots of also fun things. So I wanted to mention, so we can have, for example, very interesting phenomena that happen. So on the one hand, you can say, if I take this fluorescing light and I detect it to my detector, I can imagine doing different things on the detection end. So one of the things I could do is I could just hook this up to imagine I have a single microwave photon detector. I could just then measure, is there a photon there or not? In other words, did the atom fluoresce? Did it fluoresce or did it not fluoresce? And what you find is if you do that kind of detector, you have one kind of measurement dynamics on the system that's conditioned on this no-click or click dynamics. On the other hand, if I do this continuous heterodyne detection, the quantum dynamics is very different. It's this diffusive kind of trajectory I was talking about before. So it's quite interesting. Depending on how I detect the system, the associated quantum trajectories are very, very different. So you might say, how can this be? Because the atom is just doing what the atom is doing. It's me that's detecting it. And the quantum mechanical answer is it because these are entangled with each other. The fact that the state of the atom, the excited state or the ground state, is entangled with the microwave light field. Either I have no photon emitted or one photon emitted. And how I do the measurement on that meter, even if they're spatially separated, will then change the kind of dynamics you see in the quantum state of the atom. Okay, so again, once you have this kind of thing, you can do fun things. So I wanted to mention this paper with Pierre and also Benjamin Huard about looking at most likely paths. If I start in a particular state and go to some final state, it turns out you can even start near the ground state, be excited for a while, then come back down, and be able to analyze that kind of system. Okay, so I wanted to turn now to the main theme of this. So I've introduced for you now what these continuous quantum measurements are. And now I want to apply them to the task at hand. So here is the title of our workshop, Observability and Estimation in Quantum Dynamics. So I just talked about observability. And I want to now talk about these estimation tasks. So the Hamiltonian parameter estimation, the quantum state tomography, and the error correction. Okay, so let's start with Hamiltonian parameter estimation. So here's the basic idea. We have some Hamiltonian, and for definiteness, let's begin with just a single qubit, and there is a parameter we don't know. So in this case, suppose it's the value of the Rabi drive we apply with some frequency omega. That's a parameter sitting in my system Hamiltonian, and I don't know what that parameter is, let's say. In the experiments, actually, they dial in some particular value of frequency, but for whatever reason, maybe they get drifts in the experiment, and so we're not exactly sure what the actual qubit experience is. So we want to be able to then figure out, based on the measurements of this qubit, how we can determine this parameter. Okay, so for example, and there usually there's sort of two limits we want to be able to consider. One is efficiently. In other words, what's the minimum uncertainty I can put on this parameter? And the second is quickly. I want to do this fast for some reason. Okay. So here is the basic idea. So there are different estimation strategies. There are different ways that I can apply to take the data that comes out of my detector and then apply them to estimate this parameter that I'm interested in. And so one of the most useful ones is this maximum likelihood method, and we have some approach we call the improved maximum likelihood method. And the idea is very simple. We imagine we have some collection of data, so we have some continuous readout, so we get these results R1, R2 through Rn I was talking about before. And we take our quantum mechanical formalism and we compute what's the probability density of those results given some hypothetical value for this parameter I want to estimate, omega, capital Omega. And what I'm going to do now is I'm going to use this as a likelihood function for the unknown frequency, and then we're going to take this thing. So typically this form will take the form of some trace of a measurement operator, a state, some Hermitian conjugate, where this is typically some product of many of these measurement operators associated with these different measurement outcomes. And then I want to then take this formula and I'll maximize it. I'll maximize it over all possible values of omega given the measurement data, and that will be my maximum likelihood estimator of this parameter. Okay? And one of the ways we're able to take this formalism and apply it is we can actually pre-program the results of these imps of r's given a particular measurement result. And so each of these imps is just going to be some 2 by 2 numerical matrix. So the idea is that we'll just take each 2 by 2 numerical matrix associated with each outcome, string them together in a very fast matrix multiplication, and produce this maximum likelihood estimator. Okay? So this is for a pure case. If I want to do mixed states, I have to generalize to 4 by 4 matrices. All right, so what's the result? So now suppose the Rabi frequency is fixed the whole time, and I take this likelihood function I talked about before, so this p, I take its logarithm and plot that as a function of some frequency. What I see typically is this kind of plot. There is a nice, because this is on a logarithmic plot, or a logarithmic log likelihood, I say a nice parabola here, which represents a Gaussian distribution. And the peak of that Gaussian distribution is going to be my estimator. That's my most likely estimate for this value. And the width of this distribution will then be my uncertainty of my estimate. So that's what this approach gives you. It tells you my best estimate is this, plus or minus some uncertainty, and the name of the game is to minimize this uncertainty. Okay? So for example, here the true value of the parameter is 1 megahertz that I apply. The most likely estimate is 1.0025 megahertz. And then, so then I can ask different questions. So the uncertainty is going to be this amount, so I can see that the error, the actual error, is within my uncertainty given by the width of my Gaussian. Okay? And so what's nice about this is that I can do this all in a single trajectory because the parameter is not changing even though the state is. So I just have one long trajectory, say 1 millisecond. And then I have, so this is a millisecond. The characteristic measurement time here is 1 microsecond. And then again, and also the characteristic Rabi flop is going to be about a microsecond as well. So then I can get very good estimation from just a single run of a trajectory. Okay, this will change when we talk about tomography in a moment. But now suppose you can ask a more interesting question. Suppose the Rabi drive is not just some fixed parameter, but in the experiments we have maybe some temperature is fluctuating a little bit on a slow time scale, or somebody hits the elevator button, and you have something like this. You have a drifting Rabi frequency in time. And so what's going to happen now is, say that you have a dotted line that's the actual Rabi frequency. It has some slow drifts on a long time scale, something like that. And our task is to figure out, in a single experiment, what the drifts of that Rabi drive were. Okay? So what we imagine doing is we have a couple of different techniques for doing this. The problem with my maximum likelihood technique is that, so it turns out this is a very efficient way of doing this. This is an estimator that minimizes the variance, but typically can be slow. All right? And so you might think about faster estimation schemes that can do this on the fly. So one very simple way is I can just say, I've got some noisy data, it's oscillating in time in principle. I can just take its Fourier transform and look at the peak of that distribution. So that's a very simple but crude technique, and so this is this fast Fourier transform technique, and so I can compare this with the max likelihood technique. And so what I find is that on the whole is, yeah, so in this case, what do I have? Is imagine I have some moving time window where I want to choose to be some interval, say 40 microseconds. And the purpose of that window is I want to then use the data in that time period to make my estimate, but I don't want to use that window being too small because I don't have enough data to be able to make a reliable estimate. On the other hand, I don't want it to be too long either because then the parameter drifts on me before I'm done with the estimation. So I need to optimize that window to get the best precision. And so what these points are, this is just as my window moves, if I step it, say, in 10 microsecond intervals, these are my estimates as I move along. But what you see there is that I can do a pretty good job of tracking that frequency using this on-the-fly estimation strategy. Okay? So the idea is that this could be useful in an experiment because I tracked this for some time, and then I know exactly what the local Rabi drive was, say, an experiment between these 2 points here and here, something like that, and that allows me to get more accurate predictions. Okay. Good. So let me turn to the next topic. So now I want to think about another estimation task, which is quantum state tomography. So here I have say n copies of a state that I don't know. Generically, what's going to happen is I'm going to have some measurement strategies I apply. I make some measurements, and then I want to estimate the quantum state using this procedure. And the typical way you would do that is estimated on the left-hand side. I take my n copies and I divide them into m bunches. And for each of these m bunches, I measure one observable. So for a simple qubit, it would just be, say, sigma x, sigma y, sigma z. I measure those many times. I get some estimates of those expectation values of those operators, those observables, and I take that data and then I use some technique to estimate the state, typically something called linear inversion. Okay? And so this is the usual way you do that, and this is simple, this has lots of nice advantages, but I want to then turn this around to see if there's another way of doing it. And the other way that I'm going to do it is I'm going to have something like this. I'm going to have my system, I'm going to apply some control to it that I'm going to be able to choose, a fixed but optimized control. I'm going to do some continuous measurement, say, of one observable, say z. I'm going to collect some signal, and then I want to, just from that simple setup, I want to repeat that many times and then be able to estimate the initial state. So that's the thing. So I have continuous but fixed controls. I only do one thing. I just do the continuous measurement, I do the estimation. So the advantage is I don't have to do many different types of measurements. I just turn the thing on, repeat it many times, and that's all I have to do experimentally. But it turns out that this estimation, typically can get more complicated inversion methods to be able to estimate the state, and also it may be difficult to get all the information you need from this technique if you don't choose your controls right, for example. So the picture illustrates what happens if I have the same record, but I imagine I have two different states. What happens is I get, for example, the blue quantum trajectory, and I also get a green quantum trajectory that's different. But the thing I want to bring your attention to is that after a long enough time, these trajectories coincide. So what happens is that the measurement record essentially forgets about the initial state. It becomes uncorrelated from it. And so you only have a certain amount of time before your measurement record stops being informative about the initial state. So we can only then measure for some relatively short time before we simply lose all the information, and we have to then restart. Okay, so this is similar to basically quantum wave function collapse, where after you collapse the state, the information about the initial state is then gone. Okay, so here is the kind of thing we're interested in. So we want to generalize this from a simple qubit to something more interesting. So the proposal I want to share with you is something like this. Suppose I have a network of qubits, but they're densely packed in some tight array, and I can't measure all of them, but maybe I can only measure the ones on the boundary, so the probe qubits. Is there a way, just by measuring the ones on the boundary, I can reconstruct the state of the entire network of qubits? This is the question. And we want to answer that question, at least for simple networks, in the affirmative, and I want to give three paradigmatic examples. The first example is what I just talked about, the simple qubit. I want to estimate the initial state. The second example is, suppose I have two qubits now, but I have some coupling between them, say an XX coupling. I can measure one of them, but not the other one. Okay? And I want to figure out what the state of the other one is, supposing I can apply some Hamiltonian control on it, but not measure it. That's the question. That's what we call the remote qubit case. The other one is the full qubit tomography. I have, again, XX coupling, but now I know neither of these states. They could be some entangled state. Is it possible by making measurements on just one of them that I can infer the total state of both qubits? Okay? And here's a little summary of the model. So the idea is that we get to control these angles, the angles of the Rabi axis of these local controls, but the coupling, say, is fixed between them by some geometry, let's say, of the qubit. Okay, so that's the task, the estimation task. And how do we do estimation? So the estimation is going to be a generalization of this max-like idea I talked about before. I'm going to think about talking about the probability density of some particular trial state rho prime that I don't know, given all of these measurement data, which by Bayes' rule is proportional to this. That's our probability density. And so there are two different estimation strategies that I want to talk about. The first is called Bayesian mean estimation. That's where I sample this distribution, this trial distribution for all possible trial states rho prime, for example, chosen from some sample state space. And then I average that over, I'm going to average that over all possible physical states within the allowed region, and that's my Bayesian mean estimator. The second estimation strategy is a simpler one. It's simply called max-like. I'm simply going to then search over this space. I'm going to find the state in my physical region that maximizes the probability, and then I'm going to take that as my estimation. Okay, so this is the generalization of max-like from the simple parameter now to a full quantum state. Okay? And what's nice is that, so while sometimes linear inversion, for example, might give you trial states, estimated states that are outside of the possible bound of the quantum state, this kind of estimation by construction will never do that. I will only give a physically acceptable states by this estimation strategy. Okay? Good. Okay, so here are some of the results. So we also have some ways of trying to guide ourselves to figure out how to choose the correct controls, because if you choose the wrong controls, it turns out you don't get full information. You only get a portion of the information about the state. For example, in a single qubit, if I don't apply a drive, I can only measure the z component. I have no information about the x and the y component. So we have a couple of methods to guide us in how to do that. So one is, imagine we have some kind of commutator technique where we think about, as the dynamics continues, the idea is I want to take every bit of information on my entire state space and map it back to the measurement channel eventually. Okay, so one way of thinking about that is you take repeated commutators of the Hamiltonian with the state, and eventually I want to have every possible operator come into my measurement readout channel. The next one, I don't really have time to talk about Fisher information. That's going to play a big role later on in the rest of the talks of this workshop, and we have a lot of results using quantum Fisher information. But without telling you too much about what it is at this point, we'll just say it bounds the variance that you can take on the it bounds the variance on my estimator for any kind of estimation, unbiased estimation technique. And so it's very useful. So we can actually calculate these Fisher informations for each element of the parameter space and then plot them to figure out which value of my control I should choose to go to some sweet spot so I get basically equal information about all my parameters I want to be able to estimate. Okay? So this is the results of this estimation. This is for a simple qubit. I plot the variance, covariance as a function of time. I'm choosing some 5,000 copies to do this on. And what you see as I go longer and longer, the uncertainty gets smaller and smaller and smaller. And so what I'm plotting here is I'm plotting the estimate for 3 different times. This is in units of the characteristic measurement time. So first 0.1 measurement time, 0.3, and then 0.9 for many copies. And what you see is I can plot actually this little peanut here is like a covariance uncertainty of all the parameters of my system. And so what you're seeing, and you can construct this from the covariance matrix. And so what you see is that as time goes on, the little peanut gets smaller and smaller and smaller. So I have the 3 different estimates here. So I have the Bayesian estimate, Bayesian mean estimation, the maximum likelihood estimation, and the actual state. And you see as time goes on, these are all clustering closer and closer and closer together. Okay? So as time goes on, basically my uncertainty goes down like 1 over square root of the time that I measure. Okay, so that's showing you that we actually are able to then accurately construct this estimator. And I also want to bring to your attention some very nice results by Benjamin Huard and Pierre Rouchon's group as well. They're doing a very similar kind of technique with fluorescence experiments. So here we have in mind the dispersive measurements I was talking about before, but they talked especially about dispersive measurements for a single qubit in this nice paper as well. Okay, so let's go on. Just in the interest of time, I'm going to skip over the remote qubit and go to directly to the full 2-qubit estimation. And so again, if you choose the controls correctly, you can then estimate all 15 elements of my 2-qubit uncertainties and be able to, this is plotting the uncertainty for each of these 2-qubit operators for different values of the measurement strings. And the take-home message here is that I have to, once I choose the controls correctly, I want to have a relatively large coupling between the 2 qubits so I can facilitate information transfer from one to the other and then take that information and map it to the readout channel. But if I do it correctly, so this is, I think, with 4,000 measurement records, I can get an uncertainty, fidelity with respect to the initial state of about 0.98. And of course, if I take more trials, I can further boost that fidelity as well. Okay. So I'm running out of time, but I want to talk about one last application. So now the application is, the estimation task is figuring out where errors occur. And I'm talking about a very simple error, a 3-qubit bit flip error correction code. And the idea, usually what you would do is you have, in a gate-based scheme, you have a qubit you want to encode, a logical qubit. You encode it in 3 qubits with some code strategy, and then imagine you have some error, but if you apply then some C0 gates on my ancilla gates, I can then, by reading them off, say when the error happened and when it didn't happen. And this works great, except when an error happens, say, in the middle of my gate sequence. If I have something like that happens, then that creates a logical error that I cannot correct, and I'm done. Okay? So the idea we want to think about is doing, instead of something like this, an alternative scheme where you would, instead of doing this is called the parity measurement, where I check if the qubits have the same, 0, 0, and 1, 1, parity, or odd parity, 0, 1, or 1, 0. Instead of doing this, I'm going to imagine doing some kind of continuous parity measurement that happens all the time. So I don't have to cycle these gate sequences on and off. I just simply turn my controls on. They measure the entire time. I'm able to then still do my error correction. Okay, so this has certain differences, certain features, and I'll talk a little bit about that. Okay, so basically this is the idea. The idea is I have 2 readout resonators coupled to 2 qubits, and another readout resonator coupled to these 2 qubits. Each one of these, if I look at the amplified signal, the idea is that the even parity subspaces should be on one side, the odd parity subspace should be on the other side, so I can distinguish between even and odd parities, but not within the parity subspaces. Now this is tricky technically for this kind of qubits because of the fact that typically these even ones the 0, 0 doesn't quite overlap with the 1, 1. So there's a trick that the experimentalists are able to do where they make the dispersive shift very large, and that basically accomplishes this for you. Okay, so this is the idea. This is not just a theoretical scheme, so there's a nice new chip that's been developed. This is in Irfan Siddiqui's group. So this is a chip that implements exactly what I was talking about. You've got 3 qubits here. You've got 2 readout resonators. You also got some Purcell filters, and then it realizes this continuous parity measurement. So it has certain advantages. So there's no in silico qubits. You've got this continuous xenoprotection. As you measure the parity basis, you tend to project into the parity eigenstates, which then tends to suppress certain types of errors, and you can then detect errors in real time. All right, so what's the idea? The idea is that as errors occur, so we have some bit flip errors that occur in time, is that you can imagine starting with some no errors, say a single error occurs on the right qubit, you can think about that as mapping from one system state to another one, and then another error occurs, and you can go over to here and so on. The nice thing is if I think about all possible bit flip errors that can occur on these 2 qubits, I can't go outside of this 8-state system code space. So rather than trying to correct the errors, why don't we just track them? Let's just see where the errors occurs, because I can't go outside these 8 space. So I just imagine hopping around for some time, and then when I call the qubit for use in some computation, I'll just say, it's in state XIX. I'll decode the state from that state. So rather than trying to correct on the fly, I'll just monitor that. All right. So now I have some continuous monitoring of the parities. How can I then infer what the current state is given those readouts? Okay. And so the idea that we apply is basically a filtering technique. So you can think about a Bayesian filter, which is related to a linear von Ham filter. So I take the currents associated with my parity readouts, I plug them into this filter, and that allows me to estimate what the probability of being on any one of these nodes at a given time is. And that's then our estimate of what errors have occurred. Okay? So then the name of the game here is then to minimize the logical error rate, gamma, which is associated with this technique. Okay? So typically what you find is the fidelity has some initial drop. And this just corresponds to if you call the qubit before you have a chance to correct the error, then there's an initial drop. And then there's an exponential fall off with some rate gamma. Okay, so we want to then figure out what these rate gammas are. Okay, so what you find here, roughly speaking, is that for this Bayesian filter, the error rate goes like the bit flip error rate mu squared, which tells you the filter is working. So if it were linear in mu, that would mean you couldn't correct single qubit errors. You can correct all single qubit errors, but you can't correct 2 qubit errors that occur within your measurement time. So we have to identify all possible sources of error and then be able to then show how the filter can either correct them or not correct them and then quantify that fidelity. Okay, so again, this is some continuous technique. And if I compare that to a gate-paced scheme, the idea is that the gate-paced scheme has this danger zone where you don't want to have errors in the gate sequence, which are typically long. And so the idea is then you want the cycle time to be relatively long so you don't have too many of these repetitions. Otherwise, the probability of getting this uncorrectable logical error gets big. And so what you can see from this is that the cycle time can't be too short. And so therefore, this continuous monitoring, if you can have good quality measurements and continuous monitoring, will always do better because there's none of this danger zone region that happens. Okay, so I think my time is up. Let me just thank my collaborators that have worked on this. So on the experimental team I've been working with, so Irfan Siddiqui at UC Berkeley has been a great collaborator. Kader Murch, Washington University, St. Louis, Benjamin Huard, ENS Lyon, and then my theory collaborators as well, former students, great people, some of them here as well. And then also I've got a great group, so students have been really active on this, so a couple of group pictures. And for the things I talked about today, so Jing Yang was very involved in the quantum error correction, Luis Cortez in the quantum parameter estimation, Taylor Patty Lee in some other work on state stabilization. Okay, so here are my conclusions. We talked about 3 estimation tasks using continuous measurements. So thank you for your attention.